So we're looking at classifying matter. Our objectives today are to learn to distinguish between mixtures and pure substances, and to learn two methods of separating mixtures. In the background you see some flakes of gold and a gold pan. So the flakes of gold are these guys, and they have a different density than the sand, so you can separate them by using a gold pan. The lighter materials slosh out with the water, and the flakes of gold collect in the pan. Be sure to write down these two objectives in your note-taking guide. Classifying mixtures. A mixture is defined as a physical blend of two or more materials. So pictured as a salad bar, you can put whatever you want in your salad to make a mixture. Soda is a mixture. It has water in it. It has sugar dissolved in that water. It has your flavoring in it. And to give it the bubbles, you have carbon dioxide gas dissolved in your solution. So you don't have a slide for this, but you should add this on your note page. That soda is a mixture. Air is also a mixture. And air is composed of a number of gases, and we call it a solution of gases. And the composition of air is 78% nitrogen, 21% oxygen, 0.93% argon, and the other trace gases include carbon dioxide, which is 0.03%, neon, which is 0.0018%, and water vapor varies by how much is in the air, so it can go all the way up to 4%. A heterogeneous mixture is one like chicken soup. The composition is not uniform throughout the mixture, so it varies. You should write in your notes that there's an example, and your example is, you could just say soup or chicken soup or noodle soup, so that you know there's a bunch of different materials in it. This is a picture of rock salt with pepper. It's a mixture, and it's a heterogeneous mixture. Homogeneous mixtures have the same composition throughout. So you're looking into a beaker that has a solution in it, and you can tell it's exactly the same throughout the beaker. It consists of a single phase when you have a homogeneous mixture. It's either a solid, a liquid, or a gas. And we call it a solution. So that's an important term. Gold in the pure form is very, very soft. So usually when you have something made out of gold, it's an alloy. So when we have 24 karat gold, it's 24 out of 24 parts gold. So that's one way of defining it. 24 out of 24 parts are all gold. When you have 18 karat gold, we can say 18 parts out of 24 parts are gold atoms. And when it's 14 carats, it's 14 out of 24 parts. The other metal in it tends to make it more durable, otherwise it would wear out too quickly. So most of your jewelry is either 18 karat gold or 14 karat gold. When you have those gold alloys, they are homogeneous mixtures. We also have a homogeneous mixture when you look at a sugar solution. So it's the solution itself that's homogeneous. This is like making rock candy, so these are crystals. So that's not part of the solution. And it's just sugar and water. You can't tell it's in there except if you tasted it or you measured its density. Another homogeneous mixture is what this structure is made out of. You might notice the river in the background. I'm in St. Louis, Missouri, and I'm leaning against the arch. And the arch is made out of stainless steel panels. And stainless steel is a homogeneous mixture made of a solution of metals, which include iron, chromium, nickel, and carbon. If you wanted to separate a mixture, we can look at using the difference in their physical properties. So when you mix oil and vinegar, they separate just due to their densities and because they're different types of liquids that don't mix together. So you could use something like just pouring off the oil because it's on top. You could scoop it off with a spoon, and in chemistry we actually have a device that is like an upside down jar. So if you turn this upside down, and if we turn it upside down, let's turn upside down the one that's a mixture. At the bottom, if we had an opening down here, we would get the vinegar out, and then you could collect the oil separately. In distillation, we use that for purifying water, and the liquid is boiled to produce a vapor that is then condensed. And the apparatus looks like this. So you boil your salt water, it turns to steam, you cool it down, so you have a tube on the inside, and you have water on the outside of that tube to condense it, and then it drips into your collecting system. You could also, by the end, have this pile of salt, and you'll have pure water on the other side. So notice that the Bunsen burner is off there. Filtration is what you did yesterday, and filtration is just separating your solid from your filtrate. So that's a term I'd like you to know, filtrate, which is the liquid component of that mixture. Yesterday, you had sand in your experiment, and this was salt water. How would you separate the gases in a homogeneous mixture of air? What they do is they liquefy it. And by liquefying the air, they cool it down. So notice down at the bottom here, we have liquid air. And then once it's all liquefied, they warm it up. And the first gas that comes off is, make sure I'm going the right way, actually nitrogen, because it boils at the lowest temperature. And then your argon would come off, and then your oxygen would still be in the liquid form if it's at negative 183 degrees Celsius. Crude oil, they do the opposite too. They heat it up. So in fractional distillation of crude oil, they bring in the crude oil and they heat it, and if you look here, it tells you how many carbons are in the chain. So if I chose propane as an example, this is what the molecule of propane can be symbolized as. It has 3 C's and H's surround it. That's an H up there, with all single bonds. So that would fall into the C1 to C4. That corresponds to how many carbons you have in the chain. The lighter chains, the ones with fewer carbons, come off first. They have the lowest boiling point, and they collect that gas at the refinery. So that would be like your propane. Then naphtha is what they use like in lighter fluids. Here you have your gasoline. That's a mixture. Here is paraffin oil or kerosene, and we use that in airplanes. And then you have your diesel oils, and then you have your lubricating oils. Then you have your fuel oils for big ships and factories. And then the longest chains, this has more than 70 carbons in it, are used for asphalt and shingles for roofs. And it's called fractional distillation of crude oil. If you ever drive down to the Bay Area and you go through Richmond, you'll see some of these columns, these structures at the plants down there, because that's where they collect the crude oil and then refine it. We have pure substances. Pure substances are of 2 types. They can be elements, or it can be a compound. If you have an element, I have an example of copper, it's going to be on the periodic table, and it's just one type of atom. One type of atom. If you have a compound, it's two or more elements combined chemically. So I have another picture of NaCl there. So elements, a nice definition is it cannot be broken down chemically into simpler substances. These are bricks of silver, and you can't break down that atom anymore. In compounds, they can be broken down into elements. So you can take water, put an electric current through it, and you'll get hydrogen and oxygen. So hydrogen, and you could write H, and you would get oxygen if you broke it down. But it has to be broken down chemically. So usually that means adding heat or electricity. Oops. And that's our last slide, but this one has a chart on it. So notice that everything is matter. It can either be homogeneous or a heterogeneous mixture. So you should be able to identify that. Those can be broken down or separated by physical methods into pure substances. So you can use filtration, you could use distillation, you could use a difference in magnetic properties, you could use density differences. Once you have a pure substance, it's either an element or a compound, and if it's a compound, it can be broken down by chemical methods into elements.